No a nyní je mou velkou ctí uvítat dnešního přednášejícího, profesora Volkera Ulma z Univerzity Bayreutu, vedoucího katedry matematiky a její didaktiky a také prorektora pro studijní záležitosti této univerzity. Profesor Volker Ulm se profesionálně věnuje především didaktice matematiky a vzdělávání učitelů, především diagnostice a podpoře žáků s nějakými potížemi, například s potížemi v rozpoznávání čísel a chápání číselných operací, ale také se věnuje podpoře talentovaných žáků a užití digitálních technologií a médií ve výuce matematiky. Pracoviště profesora Ulma, on i jeho kolegové dlouhodobě spolupracují s katedrou matematiky Pedagogické fakulty už snad 20 let. V současné době řešíme společně už čtvrtý dlouhý projekt, který se jmenuje Basic Math a který se věnuje právě otázkám, kterým se bude věnovat tato přednáška. Please,
So, thank you. Hello and welcome to this talk. I come from the University of Bayreuth, which is in the south of Germany and in the north of Bavaria. It's about 300 kilometers away from here. My talk deals with students who have severe difficulties in learning arithmetic. And the main three questions I want to focus on are what is dyscalculia, or severe difficulties in learning arithmetic? How can we diagnose it? How can we see which pupils have these severe difficulties? And maybe the most important question, how can we help the pupils? How to support them? So, to the first question, what is dyscalculia, or easier, severe difficulties in learning arithmetic? I start with some examples. Mara is 11 years old and she gets the task, count forward from the given number in steps of 10. Well, the first numbers are correct: 1973, 83, 93, and then there comes a problem, 2000. She isn't able to come over this border of 2000. The 9, well, it becomes a 10. The 3 becomes a 13. And then it works again. A second example. Sarah is 15 years old, and she got some relatively simple addition and subtraction tasks, but she can't do it. If you look at the task, you see she has difficulties in understanding the place value system. If you have to add 1, where do you add it? If you have to add 100, do you have to add it here or here? It's not very clear to her, but she's already 15 years old. So that's not a primary school student, she's already 15 years old. And these students are in the focus of my talk, students who are 10, 11, 12, up to 15, 16 years old with such difficulties. To understand their difficulties, it's useful to look at the question, what is a number? I make it concrete at the number 5. What does the number 5 mean? There are two possibilities to understand the number 5. Well, this is the first finger, the second, the third, the fourth, and the fifth. So this is the finger with the number 5. 1, 2, 3, 4. This is the finger with the number 5. This is a notion of numbers that pupils develop even before they come to school. A number is a position in an ordered sequence. So we have an ordered sequence, and this is the fifth position, the position with the number 5. It's very natural to have such a notion of numbers. It's called the ordinal number notion. In the first years in schools, students also have developed another view of numbers, namely 5 is not only the name of this finger, but 5 is also the name of all together. So 5 has another meaning. It's a cardinal number. It indicates the quantity of a set, or here of my fingers. And this is a main difficulty of pupils with severe difficulties in arithmetic, that they stick to the first notion of numbers. They see numbers as a position in an ordered series, and they have difficulties to understand numbers as a quantity. A main expression to characterize these different views on numbers is the expression basic mental models. So it's a didactic expression. Pupils are expected to develop basic mental models of numbers, and these are the two main basic mental models for natural numbers. In general, a basic mental model can be described as a content-related interpretation that gives meaning to a mathematical concept, for example, to the concept of 5. So these are two basic mental models of the number 5. These basic mental models are also the basis for calculating. Let's look at the 4 ways of calculating addition. If you want to understand what addition means, a very common basic mental model is putting things together. So what does 5 plus 8 mean? You have 5 things and 5 and 3. You have 5 things and 3 things, and you put them together. And so you get an idea what means plus, what means addition. The same is subtracting. Subtracting can mean taking things away, or it can mean a difference. So 8 minus 5 also has the meaning of what is the difference between 8 and 5. Well, and if you think it multiplying, there are different situations of different structures. On the one hand, multiplication can mean you do things repeatedly. So, for example, you go 3 times to the cellar and fetch 5 bottles. So totally you fetch 3 times 5 bottles. Or you have something in an ordered spatial arrangement. For example, in such a rectangle arrangement which gives a meaning to 3.5. And finally, division has 2 meanings. Sharing means, for example, you have 15 pupils and they go to 5 rooms, and the question is how many students are in each room. Another interpretation of division is grouping. You have 15 pupils and say form groups of 5 persons, and the question is how many groups appear. So that sounds very natural, but just let us make clear to understand addition, subtraction, multiplication, division in this way requires to have this cardinal view on numbers. Everything here is grounded on this basic mental model of cardinal numbers. So if students don't have this view on natural numbers as a cardinality, they have difficulties to understand calculation. Of course, one can say if one has this notion of ordinal numbers, one can also calculate. For example, one can also add if one only has the notion of 5 is a position in an ordered series. Then adding is counting forwards. So 5 plus 3 can be solved by counting to 5 and then 3 steps further. Or subtracting, of course, is counting backwards. And applying, well, it's a bit more complicated. You have to count forwards in jumps. So if you want to solve 3 times 5 by counting, you have to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And even more difficult is dividing, because there you have to count backwards in jumps. Well, some pupils in primary school count in this way. They calculate by counting, but it's obvious that this produces serious problems. Students simply get confused, and it's not a suitable strategy for larger numbers. So these students who calculate by counting have severe problems when they go to hundreds or thousands, because counting simply doesn't work. They have problems because they don't see relations between the numbers, and they don't use the place value system. To get an idea how pupils think who only count, let's make an experiment in our mind. We all have an idea of the alphabet, A, B, C, D, E, and students who count have a similar idea of numbers as we all have of the alphabet. So just try to calculate with the alphabet. For example, to understand how a weak student who only thinks at ordinal numbers calculates E plus C, he calculates to E, A, B, C, D, E, and then to C, A, B, C, and then he has to count everything, A, B, C, D, E, F, G, H. So the result of, here I am, E plus C is H. It's a way of addition. Some pupils in the first, second, third grade do it like that. How can one subtract? Well, then you have to count backwards. So I minus D is, you go to I, A, B, C, D, E, F, G, H, I, and then you go D steps back and come to E. But if you have to multiply, it is very, very difficult. So the strategies of pupils are to learn it by heart. So they learn F times C is, well, it's R. And T divided by E is D, because D times E is T. So the translation what would be 4 times 5 is 20, and 20 divided by 5 is 4. So students who are really weak in arithmetic, they calculate in this way, they count. And over the many years in schools, they do it quite quickly. But they come to borders when the numbers become greater, because this strategy is not suitable for larger numbers. I mentioned the word place value system. I think we all know what the place value system means. Just to recapitulate it, what's the meaning of 23? Students who have this ordinal view of numbers, they say, well, 23 is the number after 22 and the number before 24. It's a position in an ordered series. The other view on this number would be, no, it's a structure. It's 23 is a structure of 2 tens and 3 ones. It's a different view, but if you don't have it, of course, you get severe problems when you have to calculate and even if you have to do higher mathematics. So the place value system is something difficult, but something very strong to do mathematics. I think we all know the characteristics of the place value system. Quantities are structured by bundles, so there are ones and tens and hundreds and thousands. And if you look at a number like 1346, each single digit has two informations. On the one hand, the position of the digit indicates the type of the bundle, and the digit itself indicates how many bundles are meant. That's very useful for representing numbers and, of course, for calculating. And students who don't have this understanding of the place value system, they are really hindered in dealing with natural numbers. So with all this background, it's rather easy to define what is dyscalculia. I can define it in this way. Dyscalculia is a severe lack of understanding of natural numbers. And this means the pupils stick to this ordinal number basic mental model and don't have the cardinal view of numbers. It's a severe lack of understanding the place value system, as I explained it just now, and a severe lack of understanding arithmetic operations. Addition means putting things together, subtraction means taking things away, etc. So this would be a mathematical definition of dyscalculia, a lack of understanding in these three areas. And the word severe means that the problems don't go away just by further learning. Well, of course, if you learn something new, you make the mistakes, that's very natural. But here is the lack of understanding so deep that it doesn't go away just by further learning in regular mathematics education. What are the consequences if students have these problems? So what happens if the school system does not care about it? I think we all can imagine students with such problems in understanding natural numbers. They have severe barriers in further understanding mathematics in higher grades. How should they understand what a fraction is, or a negative number, calculate with fractions or negative numbers, do algebra or analysis, geometry, stochastics. Natural numbers are the basis of all this mathematics. So if there are deep problems in understanding, the students are hindered to understand higher mathematics. And as a consequence, there can be psychological problems. Because if the students always does mistakes in mathematics, it's clear that this can lead to a negative self-image, even to depression, to fears, anxiety. They don't like mathematics. Maybe they even don't like school at all because this one subject, mathematics, has effects on other subjects and school as a whole. So if one is a bit pessimistic, one can ask, well, after these many years in school, what remains? The students with these problems, they have very low mathematical competences because there are lacks of understanding from primary school, the first years in school, and they are hindered in understanding higher mathematics. So they leave school with very low mathematical competences, and as a consequence, they feel restrictions in social participation, reading timetables, doing tax declarations, and of course in professional developments, because in many professions you need numbers. So that's the situation. we have children, students with these problems, and now my second question, how can we diagnose them? How can we find out in the school system which pupils have these problems and where are the specific problems of the individual? For that, I will distinguish between two types of diagnostics. On the one hand, there is product-oriented diagnostics. It's a way of analyzing only results of calculation. And on the other hand, there's process-oriented diagnostics. It analyzes how the students calculate, the ways of calculating. These are two types of diagnostics, and I will just present them to you, and then show you how can they come together. So, to the first type, product-oriented diagnostics. Usually the students simply get an arithmetic test. Arithmetic test, it's a collection of papers, for example, 6, 7, 8 pieces of papers. And on these papers, there are simple arithmetic tasks. For example, these ones. Double 39. Or double 508, or what is the half of 76, or what is the half of 340. So relatively simple arithmetic tasks, and the students are expected only to put the result in it. Second example, say how much money is shown on the picture. So it's also a test which looks at the understanding of the place value system. So you have hundreds and tens and ones, and you have to bundle the ones and write down the number in the place value system. So this is a task on the place value system. Or third example, write down the result. 7 times 80, 39 times 4. So simple calculation task. And when one as a teacher corrects this arithmetic test, one only looks at the final results and gives a point if the result is correct, and doesn't give this point if it's wrong. So it's relatively simple to correct it, to evaluate it. How is it done? Just to look at it from a higher point of view, the students get short arithmetic tasks. As I showed you 3 examples, they have 30 to 45 minutes time to do it. And an advantage is such a test can be carried out with a single student, or in a class, or in the whole grade of a school. So you can test, for example, all 5th graders with this test and don't have too much work with it. For the evaluation of the test, only the final result is checked. It's checked if it's correct or incorrect, and points are awarded for correct answers. And the total number of points, of course, gives an information on the arithmetic competences of the student. And if the test is standardized, one can even get an individual score of the student and compare it to the larger group of students of similar age, for example. So if the test is standardized, one can get the information, okay, this student is as weak as the weakest 10% of students who have the same age. The advantages, I sum it up. It's seen very simply if a student calculates wrongly, and in which types of tasks this is the case. In which types of tasks he calculates wrongly. Typically, students in the age of 10, 11, 12 years, they are not so weak in addition and subtraction, but multiplication, division are more difficult. Second advantage is the test can be carried out with a very large group. You don't need too much personnel to do this. Just give the tasks to the students and correct it. So it's a good way for screening, for finding out which students in the whole grade are very weak with respect to these arithmetic competences from primary school. But of course, the restrictions are also clear. It's not seen how a pupil thinks when calculating, what's in his mind. You only see the result is wrong, but you don't see how the pupil thinks when calculating. So you get only restricted or little information on support, how to support the student. For that, there's the second type of diagnostics. It's process-oriented diagnostics with interviews. Just an overview, and then I give you 2 examples. This means one teacher makes an interview with one pupil. The teacher takes short arithmetic tasks for calculating, but now he doesn't only look at the result, but he tries to find out how the pupil thinks when calculating. So the teacher gives impulses like, explain how you calculate, or asks, how did you calculate that? Could you explain it to me? Can you calculate it in another way? Or how do you know that this is true? Such an interview typically lasts 40, 45 minutes. And the aim is to explore the student's way of thinking, to analyze their thoughts. So, and this is of course a very valuable basis for support measures. Let's look at an example. So we have such an interview situation. One teacher is sitting together with one student, and the teacher writes on a piece of paper, 3 times 4 is 12. The teacher and the student, they have some wooden cubes, so small cubes of wood, 1 centimeter times 1 centimeter times 1 centimeter. And the teacher says to the pupil, imagine you are the teacher and you have to explain what the calculation 3 times 4 is 12 means. Explain it with the wooden cubes. Well, and one student, Jonathan, 11 years old, he puts this pattern on the table. He puts 3 wooden cubes. This is the multiplication point. And then he puts 4 wooden cubes, so we have 3 times 4. Okay, that's a clear indicator that this pupil has a very weak mental model of multiplication. What does multiplication mean? A second example, the teacher writes on a piece of paper 54 divided by 3. And he says to the pupil, tell me how you can calculate that. So Sina, who is 13 years old, writes on the paper the multiples of 3. So she writes on the paper, on the empty sheet of paper, 3, 6, 9, 12, 15, 18, 21, 23, oh no, that's wrong, 24, 27, and so on, up to 54. So that's the number she got. And then she counts how many numbers she has written. So when counting, she makes a dot over each number to mark that this number is counted. So she counts 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So the result is 18. That's a way a girl with 13 years divides 54 divided by 3 by counting in steps of 3 and by counting these 18 numbers to get the result 18. So the result is correct. So if one only would look at the result, one could say, okay, that's correct, she did it. But the way she does this is, of course, not on the level a student with 13 years should be. And you can imagine that tasks with larger numbers cannot be solved. She can count in the up to 100, for example, but she cannot do such calculations with thousands or millions, etc. So you saw 2 examples of process-oriented diagnostics with interviews. A teacher talks with a student on the question, how do you calculate this? The advantages are one gets deep insight into the student's way of thinking. One sees which difficulties the students have when they calculate. And this is, of course, a good basis of support measure. Of course, there are also restrictions because this means high effort with respect to time, to personnel, to organization, because it's an individual meeting between a teacher and a pupil for 45 minutes, for example. In Bavaria, we have a project with 40 schools. They combine both kinds of diagnostics. They try to find out which students in one grade, it's the grade of the 10-year-old students, have deep problems, and they do it in 2 steps. First, they do this arithmetic test with all students in the grade at the beginning of the school year with pupils who are about 10, 11 years old. So they do this test in the whole grade. It's not too heavy to do this. In one mathematics lessons, the test is given out, the pupils do it, and it's corrected rather simply because you only have to look at the final results. And then in a second step, they do these interviews with the weakest 6, 7, 8 pupils in the grade. So it's a 2-step procedure, and after that they have quite deep results. On the one hand, they know which pupils have severe deficiencies, and they also know which deficiencies do these pupils have. So you have the 2 information, which pupils and which problems do these pupils have. And that's of course a good basis for support. So I come to the 3rd question. If one now knows which pupils do need support, how can we organize it? What can we do as a school? And as I mentioned, we have a project with about 40 schools and about 100 teachers who do the following. So I report on current activities in the Bavarian school system. Let's look back on the definition of dyscalculia. We defined it. It's a deep lack of understanding in the field of natural numbers, the place value system, and arithmetic operations. So it's clear what has to be done. We have to develop this understanding. So overcoming dyscalculia means developing this understanding. And these are topics which are in the curriculum of the grades 1 to 3. So usually students learn this when they are 6, 7, 8 years old, but when they are 10, 11, 12, 13, you have to go back to the first years of primary school with respect to the content to overcome these deficiencies. And how can this be organized? In these schools I mentioned, they have 3 strategies. One strategy is to offer additional mathematics lessons additionally to the regular lessons. Usually it's in the afternoon. So these very weak students with in the age of 10, 11, 12, 13, they get additional maths courses in the afternoon, which focus on understanding natural numbers. So these basics from their first grades. For the pupils, it's an additional course. In such a course, there are about 6, 7, 8 students. It's 1 hour per week. 1 hour means 45 minutes per week. And usually the students go there for 1 school year. These 6 students are taught by 1 teacher, in some school even 2 teachers, so they can even divide this group. So it's a very intensive and individual kind of mathematics lessons. Some schools don't do this in the afternoon, but in the morning. So it's the same principle. It's an additional mathematics lesson, but in the morning. And the students leave their regular class and go to a room and have this additional mathematics support in a small group with 1 teacher, 1 lesson per week for 1 school year. A third possibility to organize this support, which is a bit more difficult, is to support the students during regular lessons by differentiation in class. So, for example, you have a mathematics lesson, regular, and the majority of the class is working on the current topic, but you have a differentiation in class, maybe gifted, talented students, they work on more challenging problems, and pupils with dyscalculia or these severe problems in basic mathematics, they get specific support to overcome the difficulties. So the idea is to differentiate what the students do in regular classes. So if you look at these 3 possibilities in the project of the 40 schools I mentioned, all possibilities are done in practice. Some students some schools support in the afternoon, some schools have additional lessons in the morning, and some schools support in the regular mathematics lessons. So that's the structure, and finally I would look at the content. What do these teachers do? And for that, I look at a concrete pupil, Jonathan, 11 years old. He has no problems in adding and subtracting, but multiplication is a problem. He hasn't sound basic mental models of multiplication. In his first years in school, so in first, second, third grade, he learned some multiplication tasks by heart. So he knows 3 times 4 is 12. But he cannot explain why. He cannot tell a story where this multiplication is relevant. He only learned by heart 3 times 4 is 12. And as a consequence, he cannot see relations between multiplication tasks. So he cannot see the relation to 3 times 5, for example. Here are some results from this arithmetic test. So he got this task. Fill in the numbers so that the task matches the picture. Well, and he writes 9 times 12. Well, one can suppose that he thinks as an addition. He structures it, here are 9 and 12, so 9 and 12. And here he knows 7 times 8 is 56. Maybe he learned this by heart. 7 times 8 is 56. But he doesn't know what to do with the 0. And this is too difficult. Or, yeah, okay. So that's the situation. This student hasn't good basic mental models of multiplication. He hasn't an idea what does multiplication mean. And if we want to support him, we have to go back to these basics. And here are some tasks for that. So if one organizes such a support lecture in the afternoon or in the morning, one really has to go back to the first years in schools just to build up understanding what does multiplication mean. And these are on the first side relatively simple task, but it's essential to go back to this basic understanding. So find suitable task for these pictures, mark the groups. Well, that's a task for this additional support lessons. So the student has to see what does what's the multiplication structure of this picture. The pupil has to create a link between this picture and the multiplication, for example, 4 times 5. Here another example. There are several possibilities to find a multiplication. If you look at the whole doors, you can say, well, it's 2 times 4 or 4 times 2. If you look at the windows, you can also say it's 8 times 6. So you have different possibilities. But here, it's not only the aim to write something onto this line, but to talk about this. In such a support lesson, the teacher has to talk with the students about this situation. So why is it 2 times 4? Or why is it 8 times 6? To talk about this, to build up these basic mental models of multiplication. Other tasks, rather similar. Draw a picture for each of these tasks below. So 2 times 10, draw a picture. What is the deeper intention of this? The student, maybe he has learned by heart 2 times 10 is 20, but if he has to draw a picture, he has to give meaning to this. He has to produce in his head a situation where 2 times 10 has meaning. And that's the deeper aim of all these support measures, to produce meaning, to build up basic mental models. Some other tasks from this support lectures: find a partner, together find different multiplication problems in the classroom or in the school building. So go around and look where are multiplications in the room, in the building. Draw the situation, make a photograph, and write down the suitable multiplication problem. Very important, explain why your multiplication problem fits to the picture. So again, the deeper reason of this activity is to create a link between the real world and the multiplication problem. So it's not only necessary to learn this multiplication by heart, but to create a link to the real world. The next tasks, they refer to the number line. of course, it's an aim also to see numbers on the number line and to see multiplication as jumps on the number line, for example. A very valuable tool for visualizing multiplications is this 100 dot pattern. I don't know if you work with it, if you know it. In Germany, in secondary school, really no teacher knows it, but in primary school, which is the grades 1 to 4 in Germany, this is widely used. This is very widely used in primary school to visualize, to understand multiplication. For example, if we have the product 4 times 7, the pupils have this on a sheet of paper, and they take 2 other sheets of paper. They use the first one, put it here, and the second one to put it here. And then they visualize what means 4 times 7. They link this calculation, 4 times 7, with a rectangular structure of points. I think it's a very strong visualization of multiplication, this rectangular structure of points. And this 100 dot pattern is a very simple tool to do this in mathematics education. Simply print this 100 dots on a sheets of paper and you have this tool. In higher grades, you may also calculate, for example, 13 times 17, and for that there's the 400 dot patterns. Of course, it's only larger, and with this you can also visualize larger multiplications. So with this material, the students get tasks. For example, this one, look at the dot pictures. Can you find which multiplication problem goes with each one? So the deeper aim is just to give meaning to the symbolic multiplication. And meaning means a geometric pattern. Now further activity with this 100 dot pattern. So 2 students work together, and the task is one partner shows a number on the 100 dot pattern and the other says the multiplication problem. So 2 work together, and just to extend it, can you also think of a little story that fits to the problem? So 4 times 7, invent a story. Just to have different perspectives on this symbolic calculation. Or this task, find different ways to show these numbers as rectangles on the 100 dot pattern. For example, 18. You can show 18 by 2 times 9 or 3 times 6. 24, there are also several possibilities. If you have a prime number, there's only one possibility. So the students even see the effect that there are prime numbers and numbers where you can find different rectangles. So I come to a conclusion. I showed you some typical tasks which are used in these support lectures, in these lessons. And typical activities for the students are the transfer of representations. So if you think back, what I showed you with the last tasks, all these tasks were of this type. Calculations can be represented in different ways. For example, with material, with wooden cubes or balls or whatever, with concrete material, you can you can visualize a calculation. Another way of seeing a calculation is having it in a picture. So you see this picture with the windows and the doors. It's a pictorial representation. And if you tell a story to a calculation, you have a verbal representation. So if you think back, we had the task, can you tell a story which fits to this calculation? So you have a verbal representation, and this is the symbolic representation, 4 times 7, for example. And the deeper aim of all these activities is that students give meaning to symbolic representations. When they see 4 times 7, they should be able to think of a story, to lay it with material, to draw a picture, and vice versa. If they have a concrete situation or they have a picture, they should see the symbolic representation in it. So that's the deeper reason of all these activities. Most students create this understanding in primary school in the first 4, 5, 6 years, but there are some students, and I showed you examples, who don't create this understanding in primary schools, and they need our support activities. So my last slide is this one. If one looks at all these support activities from a more pedagogical point of view, what are success factors for effective support? Or one can also say, how should we organize mathematical support lessons? Well, the basis is mathematical understanding. So as I said, dyscalculia means a lack of understanding of natural numbers, the calculations, and the place value system. So we have to focus on developing understanding. For doing this, it's very helpful to work with material, even if with elder students, because they should get links between working with material and symbolic representations. It's also necessary to work on language, to give these symbolic representations meaning with words, to see in written texts the mathematical structures. So supporting mathematics is also supporting language development. I think it became clear that mathematical support should be very individual, because these problems differ from pupil to pupil. And from a more pedagogical point of view, we also have to see the student, the pupil as a whole, not only from the perspective of mathematics, because the student may have fear when seeing numbers. He may have a very negative self-concept with respect to mathematics, because he made mistakes all his school life, and when supporting him, we also have to work on these more psychological or emotional aspects of doing mathematics. So this was my last slide. We still have 5 minutes to go to exchange. We can also do this in Czech if you would like to, and Roman, maybe you could be the moderator, or you could be the moderator. So do you have any comments? Yeah.
I'd like to ask a question. What is the efficiency of the process of the support by all the students by this way?
Yeah. What do you mean? What is the?
The efficiency.
Mm-hmm. Yeah, that's of course a good question. One can't help every student. So I told you that in these 40 schools, about 100 teachers work with students, and well, it's difficult to say when it's when the problems are overcome and when they are not overcome. But just to give you a number, roughly 75%. Yeah, just a number, yeah. But what would be the alternative if one wouldn't do that? Well, as I told it, the problems would get greater and greater. So we can help a lot of students, but not everyone.
Thank you very much.
Yeah, of course.
disappear for the whole of the, let's say, academic or like career life? Or is it something that even if you overcome it, come back and like, if you say efficiency, you get rid of it by a couple of years of extra work, and then it's like cured permanently, or is it that it's like the permanent problem for these students?
As you can imagine, both is true. So if you really build up understanding what multiplication means, and a student has understood it, that remains. But on the other hand, the teachers say when in summer there are the large holidays and the students come back from the large holidays, it seems that they have forgotten everything. So it's rather typical as learning in general.
May I ask the second question?
Yes, of course.
Is the most important thing that as soon as you find the problem by the pupil, so is the age the main thing what helps? So when you help sooner, so by the younger pupil, is the efficiency higher?
Yes, of course. Yes. Of course, it would be best to look at these problems when the students are 7, 8 years old, because that's the time when this is in the regular curriculum. And in Bavaria, there are many efforts just to support the students in their first years in school. So that, of course, that would be best, because that wouldn't produce further problems if you just tackle this lack of understanding in the second year in school or the third year in school. But this strategy doesn't work for all students in the country. So you also have these very weak students in higher grades.
They can probably be dancers. Dancers they can be, probably.
Yes, of course. Yeah, of course. But of course, it would be better to support the pupils as early as possible. But for that, you have to see it. Yeah, you have to diagnose it, and that's not really possible in a large school system, because not every single teacher is expert for this. So in primary school, there are some teachers which are experts in mathematics education, but there are also teachers who aren't. They are more experts in writing and reading, but don't like mathematics. So it's a systemic problem. Yeah. Well, perfect. Perfect. So we have 3 o'clock.
So, Volker, thank you very much for a nice and inspiring lecture.
Dankeschön.